I'm the CEO and Chief Scientist of MOBIUS Labs. Um, Today I'm going to talk about how computer vision is going to take the next leap in space applications in the next few years to come. So when you think about AI, especially computer vision driven AI, the two things that usually sometimes people think about is that it needs a lot of processing power, and also if you're using a machine learning system, it needs a lot of training data. And that's what I want to sort of share, the recent developments, that computer vision right now no longer requires that amount of massive supercomputing power to run. And also it doesn't require that amount of training data to get it right, essentially. And that creates a significant sort of opportunity and impact for space applications. So a little bit about the company MOBIUS Labs. So we are a Berlin-based company, and we are in a nutshell, if you have to summarize us, we are nerds about computer vision. And we build computer vision systems that can work very well with technical imagery. And how we sort of distribute our software is as a software development library with what we call a no-code AI, which works standalone, and it's extremely fast, and you get very high quality output with low amount of training set. So let me talk about the fast aspect, the fast and furious aspects of this. So once computer vision systems are lightweight, for example, here is an application which is detecting ships from SAR images. And the model is only 5 megabyte in size, and it runs it can process high resolution images, around 20 high resolution images per second, essentially. And this becomes very interesting in scenarios where you don't have much compute. So let me give you one more example. Here is one application that we are working with a couple of satellite operator companies. The application is cloud segmentation. So if you look at this particular slide and you see these magenta pixels, these are the pixels that a machine learning system is automatically detected as pixels of cloud coverage. So you can say that this image has more than 40% cloud coverage. This is probably not very useful for downstream monetization. So these are not the first images that you should be downlinking. So having that intelligence on board will make you help make this kind of real-time decision, what images to downlink, how can you optimize this cost, etc. We are also working with applications for real-time detections, but let me move on. Our systems work in various modalities. It works for optical images. It works for SAR images also. And you don't need any particular special pre-processing, whether it is SAR or optical. It just works out of the box. And to sort of summarize, some of the speeds that we get are very, very fast, and also the quality is very, very good. So the system can be installed in sort of hardware like Snapdragon, Jetsons, or Xilinx processors, processing at 50 milliseconds in dedicated sort of GPU instances, or it also can run in a low power mode in CPUs with, again, around 200 milliseconds per images. And the next one which I want to talk is highest quality, but with very low amount of training set. Because to train an AI model, one of the most time-consuming tasks is to collect all this data, and especially for geospatial data, this data is expensive. It's a very high resolution. So how can we train AI system with really low amount of data to get a very high quality output? So to summarize, to give a picture, here is again an application of detecting ships from SAR images. You might be seeing this, some pixels which are marked in magenta color. So these are the annotations that we gave to the system. Only 20 images were annotated, and out came a model within 3 to 4 minutes, which is able to detect ships from SAR images. And you can see that on the bottom row, there are all these images of Rotterdam harbor, and there are extremely challenging cases where the ships are docked to the harbor, it's able to isolate those pixels very effectively. And in benchmark, we are beating systems which were trained with thousands of annotated images, where we had only 20 annotated images. It's able to also pick out very specific kind of objects. So if you want to maybe build a system where you only want to detect, say, a particular kind of shapes. So this is an application where we are working with one of our partners to detect VLCC, which is very large container ships. And you only want to sort of detect VLCC, not the tugboats. Again, with very low amount of images, we are able to build these systems. Here is a small example. Again, we took some images from press. So these were the Maxa captured images of the convoy just outside Kiev. Can we play the video, please? So this is an application to count the number of vehicles, and while the video is playing, which unfortunately doesn't seems to, okay, it started playing, and it's able to sort of build this application with only 5 to 10 images being annotated and with very high amount of precision. So it's able to find vehicles which are docked both in the road, outside the road, etc. We can go back to the slide, please. Yeah, and this sort of graph shows the capability of our system versus other sort of state-of-art systems. We are able to build applications which are 10 times more accurate, which are as much accurate as legacy systems with 10 times less training set. So you can see the graph on the green is depicting our systems. On the x-axis is the number of samples required to train the system, and y-axis is accuracy. You can see that accuracy saturates very fast compared to the other systems. And one of the other popular benchmark is SpaceNet 6, which is a SAR contest, which we benchmark our system, where we are actually beating the state of art by around 0.9 percentage points. And this also introduced a new aspect, a new interesting aspect, where for building computer vision systems, you don't need to write code. You can achieve everything through a simple interface. This is what we call as a no-code AI. And I will give you an application. This is an application to estimate oil volumes from floating head oil containers. So you will see these images from various locations of the world. So these oil tankers, you can estimate approximate volume by actually looking at these images. Images which, the oil containers which are extremely full will have the top almost with this hemispherical shape. So these are closed tanks, these are completely full. And something which is nearly full looks like this. The way that we can detect is by observing at the interior shadows. And something which is near empty will have a high interior shadows, and you can actually estimate the volume to be near empty. To build this application to detect this, you can come to our system. We have a small interface. You can define what you need to do. So you upload few candidate images to train. Then you can define certain class labels. In this case, the class labels are, is it something closed? Is it something nearly full? Or is it something nearly empty? And then you can give few annotations, maybe 10 to 20 annotations, and you can train the system. And the system trains very fast, like 3 to 4 minutes, and you can see the results immediately. You can test and deploy system. So previously an application which took like a lot of data science resources, a lot of time to train, like 3 to 4 weeks of high and expert working, can be achieved using this simple interface within few minutes. and you can test and deploy. So there's a couple of other examples of how the system looks like. One other things that we work is that when we work with our clients, we never see clients' data. What we are is we are a technology provider. So all of our systems are distributed as on-prem or on-board mechanisms, and the training can be done completely sort of as a self-service basis. And the data is completely our clients. We never see the data. And if you work with us, we have very flexible pricing and ongoing support. So we have a booth here at B30. So please do visit our booth. And if you have any questions right now, happy to take questions. Thank you. So,
Thank you for the nice presentation. I was wondering if you have identified any deep neural network architecture on the back that is the best performing one that is working in a horizontal way for any kind of application that you may have, whether it is ship detection or whatever you want to detect.
yeah, so most of we have a singular model at this moment, and it actually works both for SAR and optical. When you go to multispectrals, maybe we need multiple models because we have more information. But my hope from a more scientific point of view is that these models will converge in the next 1 to 2 years, where you can actually build applications across spectrums, across modality to capture fine details, essentially. And typically, so the new grade of sort of transformer models are shown to be very promising to build these things. And there's one added advantage for space applications, because usually there is not much viewpoint difference. You will have more or less ortho-rectified images, and then you have less impact of, say, strange objects coming in your accuracy, while you are acquiring images. So it's something which is really suitable for space applications.
Thank you.
So thanks a lot everyone for attending the talk, and please do come and visit our booth. Happy to sort of discuss further. See you all.